In the lecture 10, actually, we will discuss the floating point format of binary number system. Or we can say that how we can represent a binary number in floating point format. Okay. So, when you discuss about floating point number, it's actually for most of the floating point numbers are represented in scientific notation like something raised to there will be a decimal point and some powers. Okay, so usually we'll use scientific notation, and this floating point number is also used to represent or it is capable to represent a very large or very small numbers. Okay, something like 10 raised to 23 or something like that. Okay, and without an increase in the number of bits. When you use for example 8 bit, okay, we can represent from 0 to 255. Okay, the decimal value is 0 to 255, and if you increase the bit to or if you are using 16 bit, okay, this range can we can increase from 0 to 65,000, some 535 or something. Okay, but when you want to increase a larger number, again we need to increase the number of bits, but without increasing the number of bits we need to represent a large number. So in order to achieve such kind of or in order to represent a large number without increasing the number of bits, we can choose this floating point number system. Okay, and this is also useful for representing the decimal values or the fractional values like 0.526778 into 10 raised to some 6 or something like that. Okay, and when you consider the floating point number, basically it contains three parts. The the main two parts are known as the mantissa and the exponent part, and the other part is known as the sign. So total three. So two parts, main parts plus a sign bit. So this is the usual way we will represent the floating point number. The mantissa is actually representing the magnitude of the number. Okay, the magnitude of the number is represented by the mantissa part, and the exponent part is normally the decimal point. Okay, floating point number represent the number of places that the decimal point is to be moved. Okay, just like 10 raised to 23 or something like that. Okay, that is the exponent part. We will see one example now. So for example, consider this number 241.506800. Okay, this is a fractional number, and it's contain two parts. And in order to represent this particular number in a floating point format, usually we will move the decimal point to the extreme left, so that you can write 0.2415068. Okay, so we are moving the fractional or the decimal point to the extreme left. So you will get one part 0.24 15068 and 10 raised to 9, because here you can see 3 total 6, and we are moving to the extreme left, so we can write 9, 10 raised to 9. So in this particular example, this particular portion, the fraction 0.24150068 is known as the mantissa. Okay, and the exponent part is 9. Okay, and when you write this an integer in a floating point format, this is a new usual way. We will move the decimal point to the extreme left, so that we can represent mantissa as a fractional number and the exponent is a power of 10. So when you representing an integer value, this is a usual way. We'll move the decimal point to extreme left. Okay, so we can represent the mantissa as a fractional and the remaining as a power of 10. So this is a case of a decimal number. Now we need to discuss about the binary number system. And the standard used for representing the floating point number in a computer or a microprocessor system based or a digital system is known as the IEEE standard 7541985. Okay. So in this particular format, actually they are defined three different forms, that is known as a single precision, double precision and extended precision. So the basic structure is the same in all the three cases, but the difference comes in the number of bits. In a single precision floating point number, we can use 32 bit, and the double precision it is 64 bit, and extended precision number is 80 bits. Okay, and we can satisfy the most of the number in the single precision itself. So we'll discuss discussion only to this single precision number. Okay, and all other concepts are same. The only difference is that we are using a 32 bit number format. Okay, and when you discuss about a single precision floating point number, one bit is assigned for the leftmost bit is assigned for the sign. So here you can see that this is a sign bit. This is a total 32 bit wide, and the first bit is used for the sign, and the next 8 bit, okay, next 8 bit we are used to store the exponent. Okay, and the last 23 bits, okay, out of this 32 already we used 9, so remaining 23 bits are used to represent the Mandisa or the fractional part. So this is a format we used in a single precision floating point format. Okay, and when you discuss about this 23 bits, and actually this Mandisa part can represent a 24 bit format. So here you can see that this is only representing 23, but when you write a binary number, always we will write the decimal or the number like this, 1 point something. Okay, always we'll write a 1 and remaining values. So this one is understood without writing the format. So effectively there is a 24 bits in the Mandisa, because in any binary number system the leftmost or the most significant bit is always 1. So if it is not written in the Mandisa part, it is understood that this is always 1. So we'll see one example, then you'll get more idea. So actually we are using allocated only 23 bits, but when you write the final result, you will use 24 bits, because the first digit is always a 1 in the case of binary. Okay, and when you write the exponent part, another we are actually using 8 bit, and this exponent part is also written in a special format that is known as a biased exponent. So this 8 bit value is first, or the given value, the exponent is first added to 127. So the given exponent, for example, if it is 9, we will perform 9 plus 127, and we'll write in the exponential position. So the actual exponent plus 127 is written in the format. And if you use this particular format, you can represent the minus 126 to 128. Okay, from 0 to or 1 to 255. Okay, that's where we are using the both negative and positive number. We can represent from 1 to 25, 1 to 255 by using 8 bit. So that's why we are actually adding this 127, and this concept is known as a biased exponent. Okay, and if you see, take a single bit precision point, these are the point. MSB is a sign bit. Okay, first bit is sign bit, and the remaining 8 bit is as used as the exponent. But when you write the exponent, we will use the biased exponential concept. So we will add plus 127 to the given value, and we will write the exponent. And when you write the Mandisa part, in the binary we will always write 1 point something. So the remaining 23 bits we will write here, but when you calculate the final value, you should write 1 point something. Okay, next we can discuss one example. At that time you will get more idea. So here we need to represent this binary number in a floating point format or single precision floating point format. So this in the right side you can see the 32-bit single precision floating point number. Okay, so the given binary number we can write like 1.01101 00 101. Okay, if you look at this particular, this is 4 bit, this is 4, and this is 4. Okay, and if you move this, you can see 4 plus 4 plus 8, then 12. So you can write 1 point, the remaining value, into 2 raised to 12. So you can write the given binary number like 1 point something. Okay, this is already we discussed. And next step, the number is positive, so the sign bit is equal to 0. So we got some value to represent at the sign bit, so the MSB bit will become 0. And here you can see that exponent is 12. So before writing the exponent at this particular point, we will write 12 plus 127. So we'll get 139 and the binary value of 139. So which is written here, the binary value of 139 in 8 bit. Okay, and the mantissa or the fractional part of the binary number is written here, which is actually 12 bit, but we need to represent in a 23 bit, so we will add some zeros at the last point. So the given value will represent in 23 bits. So after this one, we will add some zeros. Okay, and this is the final result, or we can say the given number, given binary number is represented in a single precision floating point number. MSB sign bit, remaining exponent, exponents in the biased format, and finally the fractional portion or the mantissa part in 23 bit. Okay, this is the usual way of representing a single precision floating point number. Okay, and next we will discuss, once you get a single precision floating point number in a computer system, how we can identify the number. So that's a reverse operation. How to evaluate a binary number that is already in a floating point format. So you can use this particular formula to calculate the actual value. Okay, so -1 the whole raised to s 1 plus f fractional portion into 2 raised to e minus 127, because exponent is already added 1 plus 127, so now we need to subtract that. And we know that fractional portion is always 1 point something, but we are eliminating that one when you write the single precision number. So assume that given single precision number is given here, so one sign bit is 1 and exponent is given and the fractional portion is given. And the first step, we can identify the sign bit, that is 1. Okay, so you can write -1 the whole raised to 1. Here you can put the sign bit, and remaining you can see that the fractional portion, actually the fractional portion contains 23 bits, but we know that after this particular one is all values are 0, so we can avoid this, and remaining values we can write, so that values are written here. Actually it is 1 plus, so 1 here, and remaining f values are written here. The last values are 0, so that's why we are skipping that 0 and we write the remaining only. And if you take the exponent part, so this is the exponential value, and if you convert that exponent value into decimal, it becomes 145. Okay, this binary sequence is equivalent to 145, so you need to write, in place of e we will write 145 minus 127. So when you do this calculation, you will get 18 here, and after, so this -1 all raised to 1, so it is a negative number, so you are putting negative number, and now we need to write 2 raised to 18. Okay, so here you can see that this is 4, this is 4 and 3, and remaining values we need to add. Okay, so this is the final answer. Okay, this is how we can evaluate the binary number that is already in a floating point format or single precision format. Okay, and now finally we need to convert this number into decimal. Okay, so the finally when you perform the binary to decimal conversion, you will get, it becomes minus 407,688 in decimal. Okay, this is a floating point number. And we can perform one more operation, one more example. We need to convert the decimal number 3.248 into 10 raised to 4 to a single precision floating point number. So first we need to convert the decimal number into binary. So 3.2418 raised to 4. So if you write that number, it becomes 32480. And if you convert that, you will get a number which is here 4-bit 4 4. So 12 plus 3, 15 bits. Okay. And when you move this fractional point to the extreme left, and if you write 1 point something, so this is the usual way of writing the binary number, fractional number in a single position. So here you can see the fractional portion, and this is the exponent portion. So 2 raised to 40. And MSB will bit push because it's always 1. So we are talking about this particular point. Okay. So we required only 23 bits to represent that. So remaining the Mandisa part will use 23 bits. Okay. If you include this one, total 24. But when you write the single precision, we will use only the remaining 23 bits because this is always 1. Okay. And you can expand the given Mandisa part into 23 bits. So 4 plus 4, 4, 4, and finally 3 bits. So total 23 bits. So you can count as a 23 bits Mandisa part. And the exponent is 14 actually. So we need to write in the biased format. So we'll write plus 127. So 14 plus 127, you will get 141. And the binary equivalent of 147 is written here. Now we can write the final answer. So it's a positive number, and here you can see the biased exponent and the 23 bit. So this is the final result which represent the single precision representation of the given decimal number. Okay, thank you.